Hey everyone. Today we're starting 10.2, which is all about the calculus of parametrics. So we're going to bust out the calculus today and apply it to parametrics. So the last couple of days you've been working on parametric equations and kind of seeing how those work and stuff like that to have x and y in terms of some other variable, typically t. So today we're going to look at what it looks like to take the derivative there and things like that. So 10.2, calculus of parametrics. All right. So the first thing, it is kind of how you would expect it to be with the derivative. If I'm going to take dy dx for a parametric, it's just going to be dy dt over dx dt, as long as dx dt is not 0. All right, so that's the first derivative, and that's something that we need to know and remember. The second derivative is a little bit different than you would think. So the second derivative is not just going to be the second derivative of y with respect to t over second derivative of x with respect to t. So it's not going to be that. Instead, we have to think of the second derivative here as taking the derivative of the derivative that we already have, dy dx. But that's really taking the second derivative of, or the derivative again of this, right? So to keep it kind of in terms of t. So what we end up having to do is take the derivative with respect to t of dy dx and then divide by another dx dt. So what ends up happening is each time you take another derivative with parametrics, you have to divide by another dx dt. So if I wanted the third derivative, we'd be dividing again by another dx dt. Each time you take a derivative, you need to divide by dx dt. So this is actually the equation that we need to know for the second derivative for a parametric. So some questions that you might be asked involving parametrics. Let's say x is equal to 2 root t and y is equal to 3t squared minus 2t. We might be asked to find the first and second derivatives and evaluate at t equals 1. Okay, so finding the first derivative, simple enough, right? We're just taking the derivative of y divided by the derivative of x. So first derivative, dy dx, dy dt over dx dt. So on this one, the first derivative, we get 6t minus 2 on the top, and then on the bottom, that's just going to be, let's see, that's 2t to the 1/2. So this is going to be t to the negative 1/2. Which you could rewrite this if we wanted to simplify it a little bit, since it's a negative exponent in the denominator. We could go t to the negative, or not negative now, positive, t to the positive 1/2. Okay, so not negative. T to the 1/2 times 6t minus 2. And we could go a little bit further if we wanted to even. We could, distribute this through so that we would get 6t to the 3/2 minus 2t to the 1/2. So those are both formats that we would want to be able to recognize this in case it were a multiple choice problem or something like that. Then, so we found the first derivative. It asks us to evaluate it at t equals 1. So at t equals 1, well, that's just going to be 6 times 1 minus 2 times 1, which is 4. Okay, so there's the first derivative. Now we need to also find the second derivative. So here we go. We've got ddt of dy dx over dx dt. So we already know what dx dt is. We found that already up here. That was t to the negative 1/2. But now we need to take the derivative of this. And this is why I actually simplified this out up here. It's much easier because then you don't have to do a quotient rule or a product rule or anything like that. If we already have dy dx written in this fashion, we can just go, okay, let's see. That's going to end up being 9t to the 1/2 when I take the derivative there. And then that'll just be minus t to the negative 1/2 on this one. And then it's over t to the negative 1/2 because that was what dx dt we had from before. And we could do the same thing here. This is really t to the positive 1/2 times 9t to the 1/2 minus t to the negative 1/2. And then we could distribute this. And we get, let's see, t to the 1/2 and t to the 1/2 is just 9t. And then t to the 1/2 and negative t to the negative 1/2 is just minus 1. Because that ends up being t to the 0. And anything to the 0 is 1. So we get 9t minus 1 for our second derivative. And if I'm going to evaluate it finally at t equals 1, it's just 9 times 1 minus 1, which is 8. So our first derivative when time is 1 is 4. Our second derivative when time is 1 is 8. Okay, so that's one kind of thing that you might be asked to do involving calculus and parametrics. The next thing we might be asked is an equation of a tangent line to a parametric curve. So let's take a look at what that entails. There's the top. Okay. So for our next one, this time we're going to have x equals 4 cosine t, y equals 3 sine t, and we want the equation of the tangent line to the curve at t equals 3 pi over 4. Okay, so the first thing that we need if we want a tangent line is we need an actual point. The second thing we need is a slope. So if I want an actual point out of this, I need to plug in t equals 3 pi over 4 to get myself an x and a y value. So t equals 3 pi over 4 gives us, for x and y values, 4 cosine of 3 pi over 4, and then 3 sine of 3 pi over 4. Which is really just, since that's negative root 2 over 2 for cosine, negative 4 root 2 over 2. And then for sine, it's positive root 2 over 2. Remembering that unit circle. So we're going to go 3 root 2 over 2. And this does simplify slightly more because we can cancel the 4 with the 2 to make it negative 2 root 2, 3 root 2 over 2. Okay, so there's our point. And now we need a slope. So for a slope, we need dy dx, which means derivative of y on the top, derivative of x on the bottom. So derivative of 3 sine t is just going to be 3 cosine t. Derivative of 4 cosine t is going to be negative 4 sine t. But we do want to evaluate this at time equals 3 pi over 4. So that means that we need to go, let's see, cosine of 3 pi over 4, like we said before, was negative root 2 over 2. So we get 3 times negative root 2 over 2 on the top. On the bottom, we said before sine was root 2 over 2, so we have negative 4 times positive root 2 over 2, which we can just cancel the root 2 over 2s and the negatives, and we just get 3/4. So that works out nicely, because now all we have to do is stick this into a line equation for our tangent line. So y minus y1, which was 3 root 2 over 2, equals the slope times x minus x1, which was negative 2 root 2, so plus 2 root 2. And we can just leave it like that. If you want to, by all means, can solve for y. If it's a multiple choice question, you can expect it to probably be solved for y. So just keep in mind that that's a format that you could see it in. Okay, so that's the second kind of question you might be asked. The third kind of question you might be asked is for points of vertical and horizontal tangency. So let's take a look at that. Last example for today, I think. Yeah. Okay, find points of vertical and horizontal tangency. This time we're going to have x equals t squared plus t, and y equals t squared minus 3t plus 5. Okay, so if we're looking for horizontal and vertical tangency, the first thing that we need is the derivative. So we need dy dx. So the derivative of y on the top is going to give us 2t minus 3. On the bottom, the derivative of x is going to give us 2t plus 1. Okay, so looking at points of tangency for horizontal, we need it dy dx such that we have it in the format 0 over something that is not 0. So we need the top to be 0 while the bottom is not 0. So what we can do is take the numerator, 2t minus 3, and set it equal to 0 and see what we get. So plus 3, we get 2t equals 3. We get t equals 3 over 2. Okay, so that would be a possible time of horizontal tangency, but we need a point of horizontal tangency. So we would have to actually go back and plug this in to x and y. Keep in mind that 3 over 2 is not going to make the denominator 0, so we're good to go on this being a time for horizontal tangency. So if I go t equals 3 over 2, let's see, my x value is going to be 3 over 2 squared plus 3 over 2. And then the y value, 3 over 2 squared minus 3 times 3 halves plus 5. I'll let you guys multiply that out and stuff, and add it together and whatnot. And we're going to move on to vertical tangency. So vertical tangency, much like horizontal tangency, except we want dy dx such that the top is not 0 and the bottom is 0. So that means that we need dx dt to be 0 while dy dt is not 0. So we're going to set 2t plus 1 equal to 0 and solve. So t is negative 1/2 for a point, or for a time of vertical tangency. But since we want a point of vertical tangency, again, we're going to go t equals negative 1/2. And let's see, we got for the x value, negative 1/2 squared minus 1/2. And then for the y value, negative 1/2 squared minus 3 times negative 1/2 plus 5. And again, on that one, I'll let you guys simplify it. But that's the idea of finding horizontal and vertical tangency. So tomorrow I will be back. We'll talk a little bit more about the calculus of parametrics, but this should be a good start for now. Go ahead and get going on the assignment. Have fun, and I'll see you tomorrow.